Okay, we'll go ahead and get started. This last presentation is an overview of AGWA for post-fire watershed assessments. Let's see, not able to advance. Oops. Okay, so how did we get here in terms of having relatively widespread use by the Department of Interior BEAR teams for using some of the AGWA tools to look at post-fire watershed assessments? And some of the premises that we came up with in terms of analyzing a watershed or two that had good observed rainfall and runoff data both before the fire and after fire is that we found changes in hydraulic roughness can explain much of the post-fire hydrologic and erosion response in non-hydrophobic soils. So AGWA provides a framework to quickly parameterize watershed models and visualize the results. And we can quickly provide watershed scale assessments for both runoff, erosion, and sediment transport at multiple points of potential risk and for all model elements, including those downstream of burned areas. So in 2011, on the Wallow fire in northern Arizona, very, very large fire, almost 500,000 acres, AGWA, with a lot of help from Shea, was the only model that produced results for the entire burned area. And then in the process between 2012 and 2015, it was used in 21 large fires. And after that, it was adopted by the Department of Interior National BEAR teams. And we defined model parameterizations for post-fire. So we defined lookup tables for pre and post-fire parameters. So the pre-fire parameters are just what you've been learning about in terms of how we use DEMs, land cover, and soils to set up the pre-fire model. And now from a post-fire model, we look again at a function of land cover and burn soil severity from well gauge basins. And given this soil severity, burn soil severity, we adjusted curve numbers and roughness in the SWOT models. And in the Kinross 2 model, we adjusted roughness, interception, cover, as well as the saturated hydraulic conductivity. And this is the rules of thumb that were suggested by Pete Robichaud of the Forest Service, that if you had a low, moderate, or high severity, you would adjust the cover by these percentages, 15, 32, and 50. And we note that K2 does reduce as a function of cover. And again, that will decrease the infiltration rates. And so for K2, we set the roughness factor for overland flow on bare soils, or to a bare soil N value of 0.011. So that's really more than an order of magnitude change from an extremely rough environment that would have existed pre-fire. That's a conifer forest with a lot of needle and debris litter on the ground. So typical application of AGWA by the BEAR teams, just a little bit of background. So BEAR teams have to come in and complete an assessment within 14 days. And that's specified by statute so that application for emergency stabilization monies has to be made with this time frame. So the first thing they do when they get to a fire is talk to the local land managers and identify values at risk. And again, values at risk might be visitor centers, campgrounds, archaeological sites, road crossings. And so what we can do with the feature that Phil noted is that we can force a discretization to the values at risk. In other words, we'll get a point shape file, as we can see over here, and we will make sure the model discretizes to those values at risk. And those are the yellow triangles here. And so we'll get a report on both flood and erosion at those locations. And because of the time factors and the way we've set up AGWA, the bear teams usually get notice that they will deploy in 3 to 6 days to a fire while the the final suppression is underway. So they have time and they know where they're going. And if they've talked to the local managers, they can identify the values at risk, and they have everything they need for a pre-fire watershed response with a design storm. So again, use the available National Land Cover data, DEM, and the soils to run your pre-fire case. So the first product that they get from both USGS and Forest Service is a burn area reflectance map, or the BARC. So they can do an initial simulation, post-fire simulation, to stratify field work and produce field verified burn severity maps. So in essence, this gives them an idea of where they should go to in the burn area to do their checks. Now, this is part of their process, is to do a field verification, but because of the first initial post-fire simulation with the BARC, they may select different areas to go to and actually do a field verification. So once they've done the field verification, they produce a verified soil burn severity map. And then again, you can simulate post-fire with the verified burn severity map. And again, you do the pre and post-fire simulation and do the differences of those and either percent change or quantitative change. And so again, this allows limited resources or stabilization funds for fire mitigation to be applied to the highest risk areas. And in the case of the elk fire in Idaho, they saved roughly $7 million. So their default position is that if there's an area that shows severe or highly severe burn area, that some action will be done to stabilize it. So again, this is what we have and some of the changes. So this is the mountain fire near Palm Springs in 2013. And this is the difference in both peak flows in percent and sediment yield for a color ramp. Again, the brighter blue and fatter the channels, the higher percent change. And then with the overland flow elements, the darker the brown area, the greater the percent change in sediment that's shown here. So the design storm that was used was a 10-year, 1-hour event, which dropped 1.26 inches of rain. And this was the initial burn severity map that was used for this watershed. And, unsurprisingly, those areas of severe burn area in red and somewhat in yellow caused the biggest response changes in a local level. But what also is important that you can do with AGWA is see if those changes that are quite high at a local level persist downstream. And if they're attenuated relatively early, you may not have to do anything in terms of protecting this road culvert further downstream. So again, this gives them a guidance to say, all right, where should I spend my dollars to increase culvert sizes, put seeding down, and that sort of thing if needed. So here's another fire, the Las Conchas fire in Frijoles Canyon at the Bandelier National Park. And this was a complex, a large complex of fires and burned a number of watersheds in northern New Mexico coming off the Bandelier Plateau. So Frijoles Canyon is this one here. And you can see quite a large area of severe burn severity. And again, we're doing pre versus post-fire simulations for a 25-hour or 25-year 6-hour storm. And their main value at risk here is a relatively newly built visitor center for the National Monument that is literally just off the stream area for this. So the hatched areas represent where rainfall was placed, both pre and post fire. And again, we see the high burn severity sort of in the upper 20 to 40% of the watershed. And again, that's giving us a large response in terms of percent change in watershed peak. And in this case, you can see we still have pretty large response in the channels. It dissipates some, but this gives them, again, an initial estimate of how large the peak is near the visitor center. And, do they have to protect that visitor center with sandbagging or those concrete K-rails? And again, this is what we found from the pre and post-fire modeling in terms of overall percentage changes. And the bottom two are the hyedographs, the design storm hyedographs. They're the same in both cases. And runoff. And again, pre-storm, pre-fire runoff, quite low. So we got a big increase in post-fire, and then also in sediment yield. And this was a useful way to, again, for the local emergency managers to display the relative impacts and the locations of those impacts. So there was a recent study that compares pre and post-fire modeling results for 4 different methods on this. One is a rule of thumb, the ROT, which is really has to be informed by local experts. The modified rational method, the HEC HMS model with curve numbers, and Kinneros in the San Dimas Experimental Watershed. And that publication is Chen et al. 2013. And I'm pretty sure that's on our website as well. And the results, are summarized here that both the rule of thumb and the modified rational method were okay with careful local calibration. And again, nothing against this, but do you have, very experienced personnel that have a good idea of how model response or watershed response will change with severe burns? The curve number method in HEC HMS operated better for pre-fire prediction, and Kinneros 2 did better for post-fire predictions. And they hypothesize that there was evidence that the pre-fire runoffs is saturation excess modeling or subsurface flow, and that the post-fire mechanism is infiltration excess, or where the rain rate exceeds the infiltration rate. So Kinross 2 only does infiltration excess with a single soil layer, but can do saturation excess from a shallow soil over rock with a 2-layer representation. So you have to go into either hopefully have local data, or AGWA does not automatically set up, let's say, a second lower soil layer. A number of assumptions have to be made about thickness of the upper levels and that sort of thing. But so what they propose is happening, that pre-fire, you've got, again, a lot of litter cover, a lot of ground cover, and that you'll have infiltration on site that might typically go down, hit a restrictive layer, and then laterally flow to a channel. So this is a slow response and a very attenuated peak flow rate. And again, this is typical in unburned areas with shallow soils and heavy litter. In a post-fire situation, again, we get runoff generation in infiltration excess where the rainfall rate or the rainfall intensity is greater than the soil infiltration rate. And again, this is more typical in burned areas with high intensity rates. And in a saturation excess case, you do get saturation of all the pore space, which eventually does lead to surface runoff generation. And again, this is more typical in wet areas, shallow water table, or shallow soil over rock. And again, they're saying that this seems to be better represented by the curve number. So, how does this hold up under looking at some actual observed condition? So this is the Marshall Gulch watershed, which is just north of Tucson in the Catalina Mountains. And they did have some, very good pre-fire data. So this is a pre-fire hydrograph on August 18th to August 26th, 1957. Big fire occurred on the 24th of July in 2003. That was the Aspen fire. So take a look at these hydrographs. Now, the storms are not the same, but they're not that much different. This storm, average storm depth, 54 millimeters, runoff volume, 10 millimeters, runoff to rainfall ratio, about 19%. And the QP is quite small. Now, contrast that to the observation post-storm or post-fire. So look at the kind of long-term base flow conditions. So they were still getting watershed response almost over 10 days. And note the difference in the extent, or the maximum number on the y-axis. So 0.16, very low rate. Contrast that again to the post-fire situation. It's up at 40 millimeters per hour. So that's, well over, let's say, a couple orders of magnitude. And also note that all of the runoff response is basically done in about 3 hours. So we've decreased the response time due to the fire from about 10 days to 3 hours. The peak rate increased greatly, a couple orders of magnitude. And again, 0.16 versus 41.4. So, the runoff to rainfall ratio is similar, but the timing and the peak rate are profoundly different. And again, we're able to, again, reproduce this by cutting down the hydraulic roughness term to a very large extent. And basically the idea is that we feel a whole bunch of that litter and much of the vegetation is burned off. So when the rain falls, it'll come off much more quickly. Another graduate student, Gabe Sidman, investigated, how should rainfall, be input to the model. So again, we often after a fire, we don't have a rainfall event. It may occur, of course, sometime in the future, but the bear teams have to do their assessment in 14 days. So, initially we said, let's take a design storm and let's put it over the whole watershed. Well, that typically puts a lot more water on the watershed than might be observed in a typical thunderstorm or rainfall environment. So, the modeling goals are, can we accurately predict or reproduce the magnitude of an event? And can we predict which stream reaches and hill slopes are at risk? So what's the best way to represent the rainfall to meet these goals or objectives? And in this case, Gabe looked at 2 fire events, one in Zion National Park, August 1, 2007, and then back to that same fire we just looked at in the Frijoles Canyon with an August 2011 storm. So again, here are the burn severity maps. And we can see smaller area was burned as a percentage of the overall watershed. And this one, a relatively large percentage of the area was burned with higher burn severity. And again, this is our outlet point of interest. And the visitor center is right here. And I'm not sure why this was chosen as a value of interest or a modeling location. So can we reproduce the post-storm flood magnitude? And, again, give us some idea of the best representation. So we were fortunate enough in both of these watersheds to get pretty good radar coverage. So we could use radar coverage to input into the model to look at post-storm response. So the green hydrograph you see over here is from the actual storm as recorded by the radar. So, radar, there are differences between radar rainfall estimates and rain gauge estimates, but, we didn't have a bunch of rain gauges. So this gives us a pretty good indication of what happened during the storm and where it happened. So we applied rainfall, uniform rainfall intensity over the entire watershed, which is typically what you do with a design storm. You might use area reduction factors, but for a quick read, this is the way to do it. We used an SCS type 2 storm over the whole watershed, which gives you a peak in the middle of the storm. So here's the uniform rainfall case in blue, and here's the type 2 storm, the red, and here's the type 2 storm just over the burned area. And again, they give you a hyeta graph that again has got a peak somewhere in the middle of the storm. So that's what these input hydrographs look like. And again, this isn't a hydrograph. This is a hyeta graph from the radar. So now let's take a look at the results. Here's what the radar looks like over the Zion area. So these are color ramp again of the rainfall depths, total depth of the storm And we can see we've got some heavy rain over part of the burned area and, lighter to medium rain elsewhere. And so the proximum duration of the event, as sensed by radar, was 1.5 hours, and it dropped about 30 millimeters of watershed. And this, if you go to the NOAA 14 information, correlates pretty well with a 10-year event. And here's where the results are. So they did not have gauging stations at the outlets of either of these watersheds. So typically in a case like this, the USGS will go in and make an indirect measurement to try to estimate peak flow using high water marks. So at North Creek, we can see using the radar, and these are the hydrographs from the model, that using the DHR radar rainfall estimate, we almost get to the lower band of the uncertainty level for North Creek, and that the uniform type 2 and type 2 over the burned area are shown here. So in the uniform case, we're not generating any runoff, but the best match appears to happen with the type 2 burned area. So that's the purple one. So when we go to Frijoles Canyon, we have a slightly more uncertain USGS indirect measurement, 25%. And we can see that the radar estimate falls right in that band. And there's little difference between type 2 area on the burned area only versus on the watershed. And that's frankly because most of the watershed burned. Again, the uniform is much lower on that. So, our initial indication is, well, it looks better if we use the type 2 on the burned area only. Yeah, and there's again, our radar estimates are very good. So here's the visitor center at Bandelier after the fire, and you can see all of the sandbags stacked over here where they were put up to help protect this visitor center. But now we're going to ask the question, does the rainfall representation change the model's prediction of high-risk areas? Even though we saw that the rainfalls from these design storms gives a much different answer than the actual event as predicted by radar. So again, for a rapid assessment, a design storm is used. And in this case, it was a monsoon storm, 2-year return interval, 30-minute storm that would drop an average of just over 13 millimeters. So which hill slopes and stream reaches have the greatest change in runoff or sediment and yield from pre to post fire? So these are, again, the color ramp results from the hill slopes and the percent change in peak value. Remember, the burn severity area is down in this lower portion of the watershed. And again, you can see that's where the action is happening in terms of changes, both in runoff and sediment yield. But again, we're going to, put the rainfall on under these same 4 cases that we've been talking about on this event. So here's our map of high-risk areas, both for the North Creek and Frijoles Canyon. And here we've got a little blow up down here. But now let's rank them. So we can rank the impact of either runoff or sediment on every element and say which is the highest one to the lowest one. And in both cases, we do that. And so this is a ranking due to the fire response again, from highest to lowest percent change. And there's a Spearman's coefficient statistic that can allow us to statistically compare rankings. So if this coefficient is 1, it implies perfect agreement in the ranking. So again, you develop a ranking for each type of rainfall input. You know, monsoon, this is the radar one, uniform, type 2, only the burned area. And we're going to compare the rankings under these different rainfall scenarios for peak rate on top and peak flow rate for sediment yield. And okay, so the brown is the rank comparison for sediment yield on the hill slopes, and the blue is for peak flow on the stream reaches. So if the area is, or if the ranking agrees well, 0.9 or 0.89 and above, it says, you know, it's just about as good as applying the actual observed event. And we can see here for sediment, we get, you know, very high agreement, not as good for the peak flow. Our lowest, I guess, is 0.46 here. And down in frijoles, again, we get pretty good rankings in terms of the Spearman coefficient. But the point is, the statistic is generally high for the design storms. So our conclusion is that the rainfall representation drastically does change our ability to accurately present the model post-fire storm magnitude. And we've shown in this study, or Gabe has shown in this study, that radar is the best method to do that. But that the high-risk areas, the predicted high-risk areas, do not vary drastically between the rainfall representations. So the overall conclusion here is that AGWA Kinross can be used to reliably predict relative pre to post-fire changes, and again, identify these areas at risk. And again, models are more reliable at predicting relative change than absolute change. So we've talked about this over and over again. You need good rainfall representation, and we've suggested to the Bear teams, now that there is getting a bigger repository of storm conditions that are recorded with radar, that it may be better to go back into the radar rainfall record and pick a storm that is a relatively large storm to test this. In other words, don't make all the assumptions that you do with a design storm, but use something for radar that will give you the actual space-time changes in an actual event. And I mean, we haven't automated that sort of selection process, but we really think this is the way to go. So again, our lessons learned from the Bear applications is that using a design storm with uniformly distributed precipitation will accurately identify the ranking from pre to post fire. However, when I say uniformly, it's in space. It's not uniform or in time, because we saw that very much under predicted. So we also saw that the Bear team benefited from the initial results. In other words, using the bark predictions in terms of helping them prioritize their field work. And that, again, these percent difference maps can help the Bear team locate values or risk levels and optimize or better optimize the design for treatments. And this has helped other agencies in terms of the Corps engineers, statewide hazard planning groups, again, identify site-specific modeling needs for emergency warning systems. And I think that's all I have.